Next, we're going to continue talking about inferences for a population parameter, where now this population parameter is the proportion of, let's say, successes in a population, such as the proportion of successes for, let's say, all possible field goals performed in a population of field goals. It could also represent, let's say, the proportion of people who will vote for a political candidate at a certain point in time. It could also represent, let's say, the prevalence of disease amongst a population of people too. So now we're going to try to make inferences about that through taking a sample. Now, this proportion of successes, let me get my red pen out here. You can think of it also as the probability of success, and we've talked about that before. This is our parameter associated with a binomial probability distribution, which we often refer to as pi. And so what we're going to do is we're going to try to estimate it through taking a sample. In our sample, we're going to calculate the proportion of successes as well. And that's going to be denoted by pi hat. You do note that I do want to point out that I often will refer to as the proportion of successes, but it could be the proportion of other things as well. It's just easier to often talk about one aspect like the proportion of successes. Okay. And then through using probability distributions associated with pi hat, we're going to draw inferences back to the population for what the true value of pi is. Now, if you want to learn more about the stuff that we're doing right here and in some additional sections that deal with proportions, please take a look at my analysis of categorical data with our textbook. I teach a whole class on working with categorical data. In here, if we have a success or failure, that's a categorical response. And essentially where we start the course off at is with exactly with what we're doing right here. Okay, so let's let y be a random variable representing the number of successes out of n possible trials. This y, as we saw earlier in the course, has a binomial distribution where the mean is n times pi. So we would expect n times pi successes on average. The variance is n times pi times 1 minus pi. The corresponding statistic that estimates pi is simply the sample proportion, or y divided by n, the number of observed successes divided by the number of trials. Now, in terms of like a random variable value for this quantity, we could replace the lowercase y with an uppercase y, and that means our statistic itself is now an uppercase Greek letter pi with a hat on top of it. Now, probably still the most used way to do a confidence interval for pi is with what's called a walled confidence interval, named after the person who developed some methods to do this kind of a interval. This is not a good one to use. We won't use it, but it helps to still talk about its development so that you have an idea of how these two other intervals that we will use, how they actually come about. Okay, so y has a binomial distribution, but one can show that y's corresponding probabilities in many circumstances can be approximated well by a normal distribution with mean n times pi and variance n times pi times 1 minus pi. And if I can approximate the distribution of y with a normal distribution, then I can use this transformation that we talked about earlier to approximate then the distribution of z with a standard normal distribution. Excuse me. So we take y, subtract off the expected value of y, and we take it divided by the square root of the variance of y. This has an approximate standard normal distribution for a large n. Generally that works, but it doesn't work as well as maybe what we've seen in the past for central limit theorem. it doesn't work as well in certain situations. We'll talk about that later. So let's do some algebra with this quantity. Let's divide both the numerator and the denominator by 1 over n. And so when we bring that 1 over n in, now we have y divided by n. Well, that is our pi hat. We have n times pi divided by n. Those n's cross out. And now we just have pi itself. And then the denominator then becomes pi times 1 minus pi divided by n. This, since we're dividing both numerator and denominator by n, this still has a standard normal distribution associated with it. Essentially what we did was essentially multiply by 1. Now, since this has a standard normal distribution, or approximate, then we can take this quantity and find 2 quantiles from our standard normal distribution and say then the probability that this quantity is in the middle of these 2 quantiles is approximately 1 minus alpha. We've done this kind of stuff before when we first developed a confidence interval for one population mean. And similar to what we did back then, what we can do is do some algebra in an attempt to only get pi in the middle of this inequality so that we can then eventually come up with a confidence interval. And so that's what I do next. I just rearrange some terms. So first, I take this denominator, I multiply it by all parts of the inequality so that now the denominator ends up being here and here, and the denominator then crosses out when I do that multiplication with the middle term. Next, I subtract pi hat from both sides, or from all parts of the inequality, I should say. Then I like to get rid of this minus there. So what I do is I multiply through by -1 for all 3 parts of this inequality. If you remember, when you multiply by a negative number, that will change the direction of your inequality sign. And so that I always have the less than part on the left side, I just rearrange some terms. I put now this down here, and put this up here, and now I'm getting to a place similar again to what we've seen before. We were working with a confidence interval for one population mean. And so if we take that stuff out of that probability and replace the corresponding random variables with their observed values, so big pi hat becomes little pi hat, now we can state a confidence interval for pi. But there's one little additional thing that we need to worry about here. Notice I still have pi right here in the inequality. I wanted to get to a point where I only had pi right in the middle. So because of that, what we're going to do is just simply replace the parameter with its corresponding estimate. And now we get a confidence interval that we can actually calculate. Now this confidence interval has the same interpretations that we've seen before. When I calculated this interval for one, let's say, data set, it doesn't mean that that one particular interval has, let's say, a 95% probability of being correct in terms of containing, in this case, pi. Rather, what that means is if I were to go out, take a sample, calculate the interval, go out, take another sample, calculate the interval. Suppose I did that 1,000 times and my confidence level is 95% for each interval, then I would expect on average about 950 of those 1,000 intervals to actually contain pi. That would be the normal interpretation that we would use. Now, there's unfortunately a problem with this interval. By doing this little replacement there of the pi with pi hat, what can happen in many situations is that instead of 950 out of 1,000 intervals containing pi, it could be a lot less, maybe 800. Maybe 700, depending upon the situation. And so when this happens, we often say that a particular interval has a problem with its coverage. How often does the interval cover or contain the parameter of interest? And this walled interval has problems with its coverage. So, because of that, it's best to use a different interval. And there are lots and lots and lots of different intervals out there. I'm going to talk about the two best of these. This first interval is called the Agresti-Cool confidence interval for pi. It was developed in about the year 2000. It's named after the people who developed it. And how this interval works is as follows. Rather than working with pi hat, let's work with an adjusted estimate of pi, which we're going to call pi tilde. Well, we still have y in the numerator. We still have n in the denominator. But now we're going to add a little bit to both the numerator and the denominator. With that then, let's find now a 1 minus alpha times 100% confidence interval for pi. By simply, wherever we saw a pi hat before, we replace it with a pi tilde. Also, where we had the sample size before in the interval, we add that same kind of adjustment that we did with pi tilde. That's your interval. This interval is better than the walled confidence interval. And what I mean by that, its coverage is closer to that 95% or 1 minus alpha times 100% level much more often than what we have with a walled interval. So when I say 95% for my confidence level, I can feel more confident that truly this kind of an interval is 95%. Okay. So why do we adjust the estimate for pi? Here's an intuitive reason. So where the interval where this walled interval has problems is when pi is close, to 0 or 1. I'm sorry. I guess we can word it this way. When pi hat's close to 0 or 1, the walled interval has problems. And so what we do here is by adding this little extra quantity to the numerator and to the denominator, what that will mean is, let's say when pi hat is about, let's say, 0.01, pi tilde will be greater than 0.01. So we're just raising it up. We're getting it farther from that, let's say, that borderline for what the true value of pi could be, which would be 0. And in a similar manner, if let's say pi hat was 0.99, then what pi tilde will do is it will be less than pi hat. It will be a little bit less than that 0.99. And again, what this is doing is moving this estimate a little bit farther away from that borderline. And what's going to happen then is that, notice how then we use that estimate throughout our equation there. And basically it was going to move the interval actually a little bit farther from that edge of what pi could actually be. And this is what ends up producing a better interval. Now there's an interesting, I guess, another intuitive understanding of this interval, or intuitive way to think about this interval. Let's say that pi is 0.05. So that means that quantile from the standard normal is going to be 1.96. Or how about we just say approximately 2. And so let's put that 2 in there for wherever we see this z sub alpha divided by 2. And look what happens. We're essentially taking our number of successes in our sample, which will be denoted by y. We're adding 2 to it. Then, with our n, we're going to add those 2 successes as well, because we have, let's say, 2 additional success observations. And then we're going to also add 2 additional failed observations, you could say. And so this is what our adjustment looks like then. pi tilde is equal to number of successes plus 2 more successes divided by the number of trials plus 2 successes plus 2 failures. Okay, so that's the aggressive-cool interval. The second interval that's better than the walled interval is what's called the Wilson confidence interval, again, after the person who developed it, and this was actually long ago, about the 1920s or 1930s. This interval actually is based upon a hypothesis test. So we have to get a little bit out of order here in the notes, and we need to talk a little bit about hypothesis tests, and then we'll come back to a confidence interval. So let's say I want to test these hypotheses. Pi is equal to pi 0 versus pi does not equal pi 0, or pi 0 is some numerical quantity, like maybe 0.1. Then the actual test statistic that's used in this situation is pi hat minus pi 0 divided by, and look at, we have the pi zeros in there, square root of pi 0 times 1 minus pi 0 divided by n. This has, as long as the null hypothesis is true, this has an approximate standard normal distribution associated with it, so we can make particular probability statements associated with the random variable version of this test statistic. And what the Wilson interval then does, it says, okay, so I know my random variable version of my test statistic should fall between these two quantiles for my standard normal, approximately 1 minus alpha of the time. So how about we look for all values of pi 0, and notice where pi 0 is in my equation, 3 different places. Find all possible values of pi 0 such that this inequality is always satisfied. And so maybe it would be all values of pi 0 between 0.3 and, let's say, just 0.5. I'm just making this up. All those values then essentially form the confidence interval. And so what one could do is actually use the quadratic formula that all of you learned about in an algebra class and actually come up with a closed form expression for what all those pi zeros would actually be. And this is what the expression is. You start off with that pi tilde, just like what we had with the aggressive-cool interval. You subtract off this quantile from the standard normal, take it times the square root of n, and then you divide that by n plus the quantile from the standard normal distribution squared. Take that times the square root of just a regular pi hat times 1 minus pi hat plus the quantity from the standard normal distribution, again, squared divided by 4n, 4 times n. That's the lower bound. The upper bound is exactly the same, but now you put a plus sign in there instead. Okay, so which interval should you use? Do not use walled interval. If I see you use a walled confidence interval, I will take off points. Now, overall, both the Wilson and the aggressive-cool confidence intervals perform very similarly, meaning if I say I have a 95% interval, they're both going to be, in most cases, fairly close to actually being 95%. I can't say exactly 95% because remember we're doing some approximations here. The advantage of the aggressive-cool is a little bit more convenient to actually do the calculation, but if you're using a computer, that's really not too much of a better benefit. The Wilson interval can be a little bit better in terms of getting close to that 95% level. If I'm stating that I have a 95% confidence level, in certain situations it can. When you're really close to 0 and really close to 1 for, let's say, what the true value of pi is, that's when the Wilson interval actually performs the worst. But you can actually do like a little bit of another change to what the interval is to make it better in that situation. I'm not going to get into the details behind why one would want to do that. If you're interested, go take a look at this paper by Brown et al. That was in the Statistical Science Journal. One advantage that the Wilson interval has over both walled and aggressive-cool definitely has is that its limits are always between 0 and 1, no matter what. Both the walled and aggressive cool interval could actually have like a negative limit, a negative lower limit. It could have a upper limit that's actually above 1. Now, on your own, think about why that would be bad to have an interval for pi that's above 1 or that it is negative. And if you're not sure, ask, please. Okay, so let's take a look at an example. In many public health studies, what's done is try to, let's say, estimate the overall prevalence of a disease in a particular population. This is done in many, many situations. It can be done, for example, to get an understanding of, let's say, how badly is a particular population infected with a particular disease. And that can then guide, let's say, government officials to make decisions about how to handle a particular disease situation. In this particular example, what we're going to do is look at the prevalence of, or the proportion of people in a particular population, the disease prevalence for hepatitis C in a blood donor population. And so a particular paper sampled 1,875 blood donors. And they tested all the blood specimens for hepatitis C. And what they found was that 42 of them were positive. So based upon this information, let's estimate what that prevalence would be. Let's perform some inferences. So we're going to do 95% confidence intervals. 42 out of 1,875 people had hepatitis C, so the overall estimated prevalence is 0.0224. If we were to find then the adjusted estimate that's needed for inference, if someone were just asking me what's the estimate itself alone, I would always use pi hat. But if I'm doing inferences, that's when this adjusted estimator can be helpful. If I'm finding a 95% interval, that means that z sub alpha divided by 2, of course, will be 1.96. Again, you could use the Q norm function to find that. And I get this adjusted estimator of 0.0234. Notice how that is greater than what pi hat gives us. And again, that's what pi tilde is always going to do. It's going to move us away from the most extreme possible values for what a value of pi could actually be. So with that then, we can find the aggressive cool interval. So we simply take our 0.0234, we plug it into pi tilde whenever we need it, go through all the math, and we get 0.0165 all the way up to 0.0302. So that's our 95% confidence interval for the prevalence or the probability of having HCV, hepatitis C, in this particular blood donor population. So what does this mean in terms of the original problem, though? I'm 95% confident that the population proportion of blood donors in this particular city is somewhere between 0.0165 and 0.0302. Again, another interpretation would be is that in 95% of similarly constructed confidence intervals, meaning you go out and repeat the sampling process over and over again and find the confidence interval, in 95% of the similarly constructed confidence intervals, I would expect the true value of pi to fall within. In terms of the Wilson interval, as you can see, the calculations get a little bit messier, but again, it's just a matter of plugging in the numbers into the correct spot, doing the math, and look at this interval here. It's almost exactly the same as we get from the aggressive cool. Okay. So let's talk about how we can do this in R then. So I'm going to set my y, set my n, set my alpha, and calculate pi dot hat. Here's some code with the walled interval. Again, we'll never use that interval in class or on any graded assignment or any kind of graded activity. But I calculated here just to show you what it would be so we can make comparisons. And so we have 0.0157 to 0.029. Let's go ahead and calculate then the Gressy-Cool. I put in my y. Here's my quantile from the standard normal. I square it. I take all this divided by 2 in terms of the z sub alpha divided by 2 part only. Then I have n plus the quantile from the standard normal, square it. Put that onto all an object called pi dot tilde, and we get exactly what we did before, 0.023. Then I find my lower bound, pi tilde minus the value from the standard normal times the square root of pi tilde times 1 minus pi tilde divided by n plus that quantile from the standard normal squared. Okay, so I do that for my lower bound, upper bound. I replace the minus that we have here with now a plus, put it all in a nice little data frame, and here we go. So compare that to the wall. So the wall is, you could say, shifted down closer to 0, and that's why in the end the wall doesn't perform as well. It misses stuff that would be a little bit higher often. When I say misses stuff, that's not a scientific term. It misses pi when pi is actually higher at times. And so we can see how that interval is actually shifted up. To do the Wilson interval, again, it's a matter of putting all these quantities into the correct syntax. I'll let you look at that on your own. Please make sure you do that. And here's our interval. Again, very similar to what we had with Gressy-Cool. Okay, so that takes us to page 10. Now, similar to other situations, I've showed you the harder way to do the calculations first. Here's the easier way to do the calculations. There's a package in R called binom for binomial. This is a package that you would need to actually install yourself if you're going to use it. And inside this package, there's a function called binom.confint. And for the x argument, you put your number of successes. For the n argument, you put the number of trials. So again, number of successes here, again, I just use it as a general term, would be the number of people who are infected with the disease. N is the number of people that were sampled. Conf.level corresponds to 1 minus alpha, 0.95 for us. And methods. Methods says, well, what interval do you want? This function could do a lot of different intervals. We want the one that's called a Gressy-Cool. We could also ask for Wilson. And if you really wanted to, you could ask for all to have them all calculated. Let's go ahead and just do Gressy-Cool and Wilson. And guess what? We get exactly as what we did before. Okay. And then there's also one more way to calculate than the Wilson interval. This will come in especially handy once we want to do hypothesis tests. There's a function similar to t.test that we've seen before. This function is called prop.test. For the x argument, you put the number of successes, or in our case, the number of people who are positive for the disease. N argument, sample size. Conf.level, I don't know why, but I put 0.95 there. I guess to be more general, I could put 1 minus alpha. And then correct equal false. Unfortunately, there is a default of correct equal true here, which will make a little bit of an adjustment to some calculations, which actually we don't need. And so that's why I put correct equal false. And if we run that, we get the same as before. Here's my interval for Wilson. Okay. So bottom page 10 then, we have some questions. So suppose that these city officials hypothesized that HCV prevalence was only about 1%. What do you think about the correctness of their hypothesis? Well, I mean, we can see that that 1% is below that confidence interval. So in a non-formal, let's say, way to do a hypothesis test here, we would say, hey, look at the confidence interval is all above 0.01. So I don't think that these city officials know what they're talking about. There's definitely evidence from this sample to say that the prevalence, the disease prevalence, is higher. Suppose officials hypothesized the prevalence was 2%. What do you think about the correctness of this hypothesis? Well, this goes back to what we've done before with other confidence intervals. In this case, 2% is inside the interval. So yeah, it could be 2%, but it could be something else. So what I would say here is that, well, there's really not sufficient evidence to indicate that what the city officials think is wrong. So let's talk about now hypothesis testing in a formal way. Now, to do a confidence interval hypothesis test, we essentially just did this. And let's say we're interested in that prevalence, that disease prevalence, or again, you could think of it as a probability of success, or again, you could think of it as the overall proportion in a population that's infected. Let's take the 1%. We're going to use alpha 0.05. Step 1 with the confidence interval method, state the hypotheses. Step 2, state the confidence interval. In actual practice, just pick either Gressy-Kuhl or Wilson. Don't do them both. I did them both here for demonstration purposes. Step 3, because 1% is none in the confidence interval, reject HO. And step 4, what does this mean in terms of the original problem? Well, there is sufficient evidence to conclude that the proportion of blood donors is not 1%. Well, how would we approach it through the test statistic method? We've talked about that actually a little bit earlier. So here's our hypotheses. We're testing whether or not pi is equal to pi 0 versus pi does not equal pi 0. But you could also do left tail, right tail tests, just like what we did in the past. I'm not going to write out all that stuff because it's just a simple extension. Please make sure you can do it. And if there's ever a question about how to do it, please ask. For our test statistic, it's based upon what we saw earlier. We're going to use this value here as our observed value of our test statistic. You should think about what critical values would be if we have a two-tailed test. As you might imagine, we have these two quantiles from a standard normal distribution. We could also do a p-value. Again, a p-measure of or what the p-value is measuring is a measure of how extreme the test statistic is relative to the probability distribution that's created assuming the null hypothesis is true. So for us, it would be 2 times the probability a standard normal random variable is greater than the absolute value of the observed test statistic. On your own, again, think about what a left tail and right tail test p-value, how you would actually calculate it. And not just, I guess, think about it, actually write it out. So you might be thinking, okay, well, so we've been using this approximation for the standard normal. Well, for Z here, when is it doing a good job? And we come to something that's really interesting, or at least I think it is from a statistical perspective and from a teaching perspective. And that is most books will tell you that, okay, if your sample size, the number of trials is greater than if the sample size times the hypothesized value of pi 0, if that's greater than or equal to 5, in other words, this would be successes, to put it in a general term, what you would expect the number of successes to be if the null hypothesis was true. If that's greater than or equal to 5, and the number of expected failures then will be greater than or equal to 5, then this approximation is okay to use. But as I say here, it's not that simple. And very interesting, this recommendation has been perpetuated in many textbooks. And a few years ago, a researcher went through these books to see where they got this recommendations from. They couldn't find it. They then looked through the statistical literature to find where this recommendation came from. And they couldn't find it either. So no one can find the original person who came up with this recommendation. So here's my recommendation then. And that is simply look at the sample size, the number of trials, and pi 0. Now, as long as you have, let's say, a moderate to large sample size, and pi 0 is not too close to 0 or 1, you should be fine. But as you get closer and closer to 0 or closer and closer to 1, you basically need a larger and larger and larger sample size in order for this normal approximation to work. And so in the end, what you should do is when you have a smaller sample size and you think that pi 0 could be close to 0 or 1, got to be careful. This normal approximation might not work. And what I would do instead is look at some other inference procedures that where this normal approximation is not used. These other inference procedures are referred to as exact inference procedures. If you want to know more about those, take my course on categorical data analysis, or take a look at my book. Okay, so let's take a look at this particular situation. Now, obviously, pi 0 here is 0.01, but I have a pretty large sample size, so I'm not really concerned about the normal approximation here. So what we're going to do is do a hypothesis test for pi equal 0.01 versus pi does not equal 0.01. Again, we've already calculated our pi hat to be 0.0224. Then let's find the test statistic. So I put pi hat minus the hypothesized value of pi divided by the square root of that 0.01 times 1 minus 0.01, and then divide by 1875. Do the math, you get 5.4. Wow, that's large. And if we look at that, well, we could also find our critical values as well. We've found this critical value many times before. It's 1.96 plus or minus. If we graph it out, take a look at this. So my test statistic is falling way on the far right side of my distribution. So what this is telling me is that if pi was truly 0.01, it would be very unusual to observe 42 people with HCV out of 1,875. It would be very unusual. So because of that, since 5.4 is greater than 1.96, let's reject HO. Thus, there is sufficient evidence to conclude that the proportion of blood donors infected with HCV is not 0.01. P-value. So what this p-value is just looking at now the area underneath the curve instead of looking at where you are on the x-axis. That's it. The p-value is the probability, that should be a capital Z there, 2 times then the probability that a standard normal random variable is greater than 5.4. That probability, as you might expect, is extremely small. We can find that probability as we've done before with the p-norm function. If one wanted to, one could actually do it by hand and actually do the calculation via integration. Then we can state alpha 0.05. Well, because the p-value is less than alpha, reject HO. Just as a reminder, I always expect to see statements like this. Why are we rejecting HO, even with the test statistic method? Okay, so how else can we perform this calculation than in R? Well, we saw that prop.test function earlier. And so what we can do is add an argument for alternative equal two-sided, which is actually the default, which tells our, okay, we're doing a hypothesis test. It's going to be a two-tailed test. And look at our p-value here, exactly as what I showed you above. But let's take a look at this here. This is actually our test statistic, which is actually labeled a little bit differently. Well, what R is doing for this particular problem is not using a standard normal distribution directly. Rather, it's using another kind of distribution called a chi-squared distribution with 1 degree of freedom. We're going to learn about those shortly. All this is another probability distribution. And it just so happens, it just so happens that one of these random variables, a chi-squared random variable with 1 degree of freedom, is exactly the same as a standard normal random variable squared. So what we could do here is to take that 29.12, take the square root of it. Okay? That's our test statistic. Now, of course, we need to know, well, is it going to be the positive or is it going to be the negative square root? And the way to do that, to make that decision, is you come back up to your test statistic itself and you look. Here's pi hat. It is bigger than the hypothesized value of pi, so thus I have a positive value. If instead pi hat was less than this 0.01, of course, then you would have a negative number. So that means z will be negative. And so then you would make that corresponding adjustment if you're just using prop.test itself. Okay. So some notes here. This is page 16. So the confidence interval method can actually give a different hypothesis test decision than the test statistic and the p-value methods if aggressive cool that confidence interval is used. It's unlikely that it will happen, but it is a possibility. Now, well, what if the data that we have wasn't already summarized into this, let's say, the number of trials, the number of successes out of a particular number of trials, or what we had in our HCV problem, the number of people infected out of the number of people who were sampled. What would you do then? So typically in this kind of a situation, what you will have is a bunch of zeros and ones, where zeros will be, you can say failures, ones will be successes. For us, ones would be who's infected, zeros would be who's not infected. And so here I have 1,875 ones and zeros combined. So you might get your data in this format. And so what you'll need to do is now transform it to a number of successes and a number of trials format. How do you do that? Well, one way is to use a function R called table. And so let's say if all these ones and zeros are in raw.data2, I use the table function with it, and now we have summarized simply the number of zeros and the number of ones. Also, since I'm using ones and zeros, if I want to find how many ones I have, well, just use the sum function. Let's sum them up. And once you have that, then what you can do is use that information, to find what y is, to find what n is, and then use prop.test. So if you notice here with this table of raw.data, suppose I save it into an object, for the lack of a better name. What is returned is actually a vector that has two elements in it. And so I can pick out the first and the second elements as needed to do the math. Or I could just immediately go directly with the results from table and pull out that second element. That's what I did there for y. I did a similar thing then with n as well. Okay. So then that concludes then this section on doing inferences relative to a population proportion, or you could say equivalently, let's say the population probability of success, or you could also think of it as the overall prevalence of something in a population.